Hello, in this video I'll be showing you how Richard Feynman's technique of integration, otherwise known as the Leibniz techniques, or differentiating under the integral sign. So basically you use this technique when you get really nasty integrals like I've got up on the Word doc here. The integral from 0 to 1 of x to the 7 minus 1 divided by log x dx. You can try using it by parts or any substitution stuff, but it will be very unsuccessful and very painful. So the whole idea about this technique is basically adding in a parameter and basically letting the integral be a function. So this is how you start it, is you let this integral be a function, let's say of alpha. So we'll go L of alpha is equal to the integral of 0 to 1 over x to the 7 minus, you put the alpha up here where the 7 is, over log of x dx. So by defining this parameter, this integral here is now ln of 7. So we put the alpha where the 7 is. So this whole thing now is a function. Whoops. And basically what you do now is you take the derivative of this new parameter with respect to itself. So you go L dash of alpha d over d alpha over the actual integral over x to the alpha minus 1 log of x dx. Now what you do now, Leibniz techniques, basically saying if you do this, you basically you can bring it inside the integral and turn it into a partial derivative. So I'm just gonna write our next line. So L dash of alpha is equal to the integral from 0 to 1 over the partial derivative with respect to alpha of this whole thing. Basically, a partial derivative lets every other variable equal a constant except for the variable you're differentiating with respect to. So our x's in here are now constants. So this becomes very easy to differentiate. So I'm just going to rub out some of the stuff up here. I'm going to move some stuff around. Move that a bit up there, make that a bit smaller as well. Hopefully you can still read that. So L dash of alpha, we're just going to break up this little bit, so we'll have here x of alpha over log of x. I'm just breaking this up so it's easier to see what's happening. Oh, that's not x, that is alpha over log of x dx. This entire thing, since it's the partial derivative with respect to alpha, this whole thing turns to 0. So we can rub that out now. And recall, when you're taking the derivative of an exponential, recall if you want the derivative with respect to x of 2x, it's equal to log of 2x. Therefore, when we take the partial derivative with respect to alpha of x to the alpha, we get log of x to the alpha. So applying this knowledge to this derivative inside the integral, we can go the integral from 0 to 1. When you diff this, you get log of x to the alpha over log of x dx. And of course we've got like things on the top and bottom, so we can cancel that out. So we're left with L dash of alpha is equal to the integral from 0 to 1 x to the alpha dx. That looks a lot nicer, but we still have this parameter involved. So you might be getting a bit confused saying, oh, how do we get rid of that? Basically, we now got to get back to L. We've got to get back to L of alpha. So the way we do that, we'll just evaluate this integral with respect to x and treat alpha as just some constant, which it is in this case. So I'll just get rid of that and I'll move some stuff around. So we'll just rewrite this. We'll integrate. So the way we'll integrate, recall the power rule, n plus 1 divided by n plus 1. So that's the power rule for integration, just with normal stuff. We'll do the same thing down here. So we'll go, it'll be equal to x of alpha plus 1 over alpha plus 1 to 0 and 1. We'll sub in the 1 where the x is, so we're L of alpha equal to 1 over alpha plus 1 over alpha plus 1 minus, and this whole thing turns to 0 because you put the 0 where the x is and divide by 0, 0. Now here's another trick. Any number, 1 to the power of any number is just equal to 1. You can have 1 to the power of a mole and it'll be equal to 1. No matter what number up here is, if 1 is its base, it will always be equal to 1. So using that little trick, we can simplify this top of the fraction and just say it's equal to 1. So we're just going to rewrite that now. So we have L dash of alpha equals 1 over alpha plus 1. Alright, if you want to take some notes down, I recommend doing as you go because I'm going to be rubbing out as I go as well. So I'm just going to get rid of this stuff now. Over here. And I'm going to move these ideas over here, make them a bit smaller. Right, now we've got to find L of alpha, because our function up here, L of alpha, was equal to the integral of 0 to 1 x of alpha minus 1 over log x dx. So we'll just integrate with respect to alpha. This is a pretty easy integral. That turns into a log. So we've got L of alpha equal to log of alpha plus 1 plus c. Now we've got L of alpha up here and L of alpha up here. So we're just going to equate them for a second. We've got L of alpha plus 1 plus c is equal to this integral here of x of alpha minus 1 over log of x dx. Now we got to find our c value before we even finish this. So we're just going to let alpha equal to 1. Oh no, not 1, 0. 0. So we get L of 1 plus c equals the integral of 0 to 1 over x to the 0 minus 1 over ln x dx. Log of 1 is 0, so that disappears. Up here, x to the 0 turns to 1, so this top part of the fraction up here turns to 0. So therefore our c value must be 0, because this whole side will be 0. Right? So now we know our c value is 0. We can rub that out now and just move that a bit closer. Right, we're almost done. So this was L of alpha. The integral we wanted to solve was L of 7. So all you got to do to finish this off now is let alpha equal 7. Hence the integral of 0 to 1 x to the 7 minus 1 over log of x dx is equal to log of 7 plus 1, which is equal to log of 8. Thank you if you found this video helpful. I'll be posting another example using Feynman's technique of integration. I'm sorry if I was rubbing out as you're copying down notes. It's just I'm very limited with my space on this Word document. Alright, thank you.